So we left off last time. We had just finished installing our air blast and our parts catcher on the carriage of the TL, and we were going to let the operator run the machine for a few days to make sure we had all the bugs worked out. We didn't have any chip accumulation. We were catching all our parts that we needed to. We let the operator run it, and we had to make a few adjustments to our air nozzles. But we finally got it where the operator could run the machine just like the robot will. I found in my personal experience, from this integration, from other integrations we've done, the largest issue we run into is chip accumulation, either on the tooling or the work holding. So it's better to go ahead and get those problems solved in the beginning rather than have to troubleshoot them on the back end when the robot's in place. All right, guys, now we're going to show you the actual integration of the UR to the Haas lathe, which I'm pretty sure is why you guys are watching this video in the first place. The first step to this, we're going to decide which IOs we're using and go ahead and label them. So we go to our installation tab, we go to our IO setup. In this case, we're using digital output 0 and 1 and digital input 0 and 1. You want to go ahead and label something appropriate to the process that's going on. So you can see the labels you use here on the IO tab. You want to make sure to label your inputs and outputs something describing what they're actually doing, because that's going to come up later when you're actually writing your robot program. We're using 2 inputs and 2 outputs. For our particular situation, our outputs are to open the collet and to press the cycle start button on the machine, and our inputs are to tell the robot when the cycle is complete and when to release the part. Most typical applications, you'll only use 1 digital input. That's because you're swapping, or you're taking out your finished part and placing your raw material in the same operation once the cycle is stopped. But in our case, because we're ejecting it into a bin, we need this extra input signal to tell the robot when to release the work holding. We've explained all of our 4 inputs and outputs. Now we're going to remember, each one of those inputs and outputs takes 2 wires. So it's a total of 8 wires that we have to hook up. We're going to start with our cycle start button. The first thing we're going to do is hook 2 wires, one to each side of our cycle start button, into the output of our relay. This is a 24-volt relay because our robot controller uses 24 volts. So we're controlling this relay with the 24 volts out of the controller. So in most cases, we would go ahead and install this relay either in our robot control box or a machine controller. The reason being is that this cycle start button on this Haas is ultra low voltage. So I've learned that you tend to develop an inductance in this wire as it passes by the screen. So we want to keep it 24 volts up until this point. The output side, or the short side, the low voltage side of our system, we want to keep as short as possible to prevent any interference in our signal. We're going to then run our wire from the input of the relay all the way back down the arm of the machine, because we don't want it to get tangled in our tooling, back to our robot controller, to the spot that we indicated, digital output 1, as you can see right here. Now note, these pop out, so you don't have to wire everything up inside the controller. You can pop them loose and use the screws right there. Our next I/O connection was our digital output to open the collet. So an operator would simply flip this valve open or close to open the collet. But the robot's not going to do that, so we have to do it electronically. We're going to use this air solenoid valve. And it simply works by, we put air into it here, and it has a plunger, and it's either going to output air to the open side or the closed side. When we apply power, it will move the plunger up or down and select which way it's going to go. So our choice now is, do we want to have the collet open when it's powered or closed when it's powered? And we elected to go for open when it's powered. That way when the robot shut off, the collet remains closed, the part will stay in there, and that's just for safety reasons. This hooks up much like the relay we did before in the control panel. It uses 2 wires that hook to the air solenoid, and then we run the wire back around the back side of the machine and into our robot controller and hook the 2 wires to the digital output 0. So the last of our I/O are our 2 digital inputs coming from our machine. So we're here at the back of the electrical cabinet, where we're going to hook up to our M relays, specifically M22 and M24 in this case, just like we did our air blast. We're going to hook these wires in and run them around back to our control box to digital inputs 0 and 1. So now that all of our digital I/O connections are made, the integration portion of our cell is pretty much complete. All we have left to do before we start the testing process is write the program. I'm not going to get too in-depth into the programming of this application, but I will run through the logic one time. First, the robot will rotate over the table and pick apart using the Robotiq wrist camera. Once it has a part in the gripper, it will rotate back around in the machine and wait for the part release signal. At this point, the part will be complete and the tube to catch the part will be in line with the collet. The UR will then open the collet and the part will be ejected into the bin. Once the part's caught, the carriage will move to the back of the machine and the part complete signal will be activated, allowing the robot to load the next blank. After clearing the machine and getting close to the collet, we'll use the integrated force torque sensor to insert the blank into the back of the collet. It will then close the collet and open the gripper. After exiting the machine, the UR will electronically press the cycle start button. Once the machine has begun the next cycle, the robot will rotate back around and use the camera to take another image and grab the next blank. This cycle then repeats over and over until there are no more parts left on the table. So there's three notes I'd like to make about our setup. First of all, the tape on the table. This is to indicate the field of view for the camera when we're over the snapshot position. This is for us internally, so we make sure we don't put a lot of parts randomly out throughout the table that can never be picked. The second thing we'd like to add is the tape on the gripper. We use this before we swap the fingers out when we're setting our TCPs to indicate which was gripper 1 and which was gripper 2 because we kept getting them mixed up during that process. The third thing we need to note, once we do a little more testing and get this proven out and fail safe, we're going to go ahead and put all these exposed wires in some conduit. It's just a good practice. In years past when we were doing testing, a heavy part would get dropped on a wire and cut it. We have to go back and rerun that wire. It's just the safer way to do things, honestly the right way to do things. So we've gone all the way from unboxing to full integration with the Haas CNC lathe. I hope this answers any questions you guys have about robot communications or about communication with Haas, but it's not just applicable to Haas machines. You can use it across many different machine types. I know this is what I needed when I first got started. I didn't have a clue about how to hook these things up. If you like what you saw, please like, subscribe, check us out, waltmachine.com, and thanks for watching.